Good morning, everyone. Always good to be back at UKNOF. And so, as James mentioned, I'm David Murray from Arista Networks. And I'd like to talk about two new exciting optical standards, or at least I think they're exciting, which are ZR and ZR Plus for 400 gigabit Ethernet. So if we look at the range of optical standards and connectors and cables that you might be looking at today, there's a lot of them. In today's presentation, we'll be focusing on just these two in the top right-hand corner there. So to reiterate, 400 gig ZR and ZR Plus. So these are focused on longer reach connections. Some of you may have been frustrated with 100 gig, that natively there is not a kind of metro reach or longer reach connection than we had with 100 gig ZR, I should say. But we do have that now with 400 gig. So 400 gig ZR, starting off first. ZR is really focused on the metro. So we're kind of talking in the double-digit kilometer range, so maybe 40, 80, maybe 100 kilometers. So look at the specifications of this new standard. We have a channel range. So typically, in fact, almost exclusively, your ZR transceivers will be tunable, and they'll be tunable in this range, roughly 191 to 196 terahertz range. And then within that grid, we have either, or you can choose either 100 or 75 gigahertz spacing. Typically, that's going to be presented on regular duplex LC connectors. And you'll notice actually the transmit power from the transceivers we have available today is actually relatively low power for a long reach connection. So kind of looking around minus 10 dBm. And as you'll see, that may require boosting for longer reach. That's typically because of the form factors this standard is going in. So the form factors of typically QSFP DD and OSFP have thermal limitations, they have cooling limitations. That really explains why the transmit power is maybe lower than you would expect. To conform to this standard, we do need to meet some minimal OSNR, that's optical signal to noise ratio, that I'll touch upon, and we do need to have a maximum tolerance on chromatic dispersion of 2400 picoseconds per nanometer. So typically, the fiber we're going to be running our ZR and ZR Plus on is of course single mode, and it's also OS2. But within OS2, I believe there are two different ITU standards. So there's G652C and G652D. So G652D is the one you want, which has finer tolerances, and you'll see here we need to be under 0.25 dB of loss per kilometer. And ideally, we want to be kind of around the 17 picoseconds per nanometer range in chromatic dispersion. So for those of you not familiar with these terms, chromatic dispersion is simply the fact that different wavelengths of light move at different speeds. So even if we're using a particular channel, within that, let's say 100 gigahertz channel, the shorter wavelengths of that light are going to travel faster than the shorter wavelengths of that light. Therefore, a nice impulse pulse, as you can see here, which started off as a nice square wave, will become a more rounded wave. And we don't want too much of that chromatic dispersion for our link to be active and error-free. Likewise, that and other imperfections in the link can cause noise, and so we need a minimum optical signal-to-noise ratio. So that's, as you can see here, we don't want too much noise on the link. And there is a direct relationship between that and the bit error rate of a link. So bit error rate is simply the number of errors out of the total number of bits we're sending down that link. So in the title of this presentation was real-world examples, and so we do have a real-world deployment of this with a customer in Turkey. This is, I will admit, an approximation of where we think the fiber goes, and you'll see here we have two links to demonstrate ZR on. So there's a 40 kilometer link approximately and an 80 kilometer link. So we've got our shiny new transceivers, we plug them in. What do we need to do to configure this? Well, surprisingly, not a lot. It has the look and feel of a regular transceiver configured as normal at 400 gigabits. Differences here is, as mentioned, they are tunable, so we do need to tune to our desired channel. So in this case, we have two links. So one link you can see here is configured at roughly 193.1 terahertz, and the other at 193.3 terahertz. The large numbers here, I think, are configuring it in gigahertz, not terahertz, so you need to add 1,000. So this is an Arista device, so as it happens, for our vendor, we do have a line system that plugs into a transceiver. So you'll see here with the actual optics themselves are connected to Ethernets 34 and 35. And we actually have this weird device in Ethernet 36, which is not a transceiver. It's actually a line system that is using the transceiver for power and configuration. So the idea behind this is with a splitter cable, we can actually multiplex up to 8 400 gigs passively using ZR down a single fiber pair. So if you can do the maths, 8 times 400 is 3.2 terabits. So yeah, as I say, links seem to be up. They say they're connected. Naturally, the transceiver that is not a transceiver is error disabled. That is to be expected. So we've got our link up. What are we going to be looking for in terms of statistics and monitoring to verify that this is as we expect? Well, first line in yellow here you can see is the post-FEC error frames. So this is after we've performed FEC, FEC, that's forward error correction. And as you can imagine, we really want this to be 0. So if we have post-FEC errors, that's really not good. We need to look into that. I mentioned the importance of chromatic dispersion. So this is the total chromatic dispersion across the 40-kilometer link. And if we know the rough chromatic dispersion of our fiber, which is 17 picoseconds per nanometer, and we did some GCSE A-level physics, we can actually divide that by 17 to get a rough approximation of the link length, which in this case is roughly 39 kilometers. And likewise, we can see the laser frequency we configured. One other point to note here, which is not in yellow, but this first metric at the top, the case temperature, as mentioned, does have thermal and power limitations. This is running at 66 degrees. This is, I believe in this example, it was a QSFP-DD, which is the smaller of the two form factors. It may be that the larger form factor, the OSFP, has a little bit better cooling limitations there. And then on the power, as mentioned, we do need a line system for this. And so the little line system here, which has a booster and a preamp, is taking that transmit power from the transceiver, which was minus 10 dBm, and that's lifting it up to 9 or 10 dBm there. So the booster is performing that, and likewise on the receive side, we do have a preamp as well. So you'll see those numbers are much higher than that initial transmit power. Otherwise, all looks good. So that was the shorter of the two links. That was the 40-kilometer link. How does that look like for an 80-kilometer link as well? Well, the good news is we still don't have any post-FEC errors. Always good to see. Chromatic dispersion in total is a lot more, roughly double, which is what you would expect for double the link length. So again, if we do that calculation, we divide the total chromatic dispersion by 17 picoseconds per nanometer, and we actually get a rough approximate link length of 81, which is actually, yeah, it's a good amount of distance given the fiber is not very good. For some reason, obviously there are many variables, but you can see the transceiver here is much cooler. It's only 58 degrees C instead of 66 degrees C. So again, nothing too much to shout about in the light levels here, kind of as we'd expect, apart from you'll see, because we are really pushing the length of this link now, we do have very high attenuation. So in one direction, interestingly, not both, we can see we have a warning on the bottom here, and that's because the optical receive power is just over minus 20 dBm, and the actual low alarm threshold is minus 21.94. So we're getting quite close to that. I don't think it was the best fibre in the ground for this particular link. So for that forward error correction, we do have certain loss margins. So there are two types of forward error correction that we can run. They're both using forms of Reed-Solomon error correction. There's CFEC and OFEC. So CFEC is a bit less tolerant, so you probably want to use that for shorter links. So that's 100 kilometers at 0.25 dB per kilometer of loss, for a total of 225 dB loss threshold. But if you're using OFEC, you can actually get away with a 30 dB loss threshold to get potentially up to 120 kilometers if you've got good fibre at 0.25 dB per kilometer. As you can see, we did not have good fibre, and so on that 81 kilometer link, we actually had a total loss of nearly 30 dB, which translates to 0.37 dB per kilometer. So really not the best fibre in this case, but still worked at approximately 80 kilometers with 0 post-FEC errors. So in summary, to look at ZR, which is the first part of this presentation, I think it's a really good point-to-point solution for the metro. And so in the UK, that probably translates to London and the South East. Not going to be running this to Manchester. But it is a point-to-point solution in the sense of you don't need ROADMs, you don't need inline amplifiers. There is the booster, which we have in a form factor. I'm sure other vendors have other alternative offerings. You can, in theory, use this with an external line system, but I would suggest speak to your line vendor to validate that. So that's the first part, which is ZR, really focused, as mentioned, more on the metro. And then we also have ZR Plus, which can potentially do longer distances. So ZR Plus really came from a multi-source agreement called OpenZR Plus. OpenZR Plus is really a merging of the ZR standard, that is the 400G-ZR standard, with something called Open ROADM. And so part of Open ROADM was the need for 100, 200, and 300 gigabit Ethernet links as well. And really that's merged into what is now OpenZR Plus, or colloquially known as ZR Plus. The interesting thing about ZR Plus is, compared to ZR, ZR was a single standard. Yes, we configured the frequency of the channel, but really there was one mode. Within ZR Plus, there are many modes, and so this is something we pulled from the Smart Optics datasheet here, showing 14 different application modes. And really the idea is you can configure your application mode based on the use case. So what you'll see at the top here, the first three, are essentially variants of ZR that we were just talking about. So that can give us a native 400 gig link. You'll notice channel mode 3 here can also do breakout. So you can have one optical connection that is 400 gig optically, but can actually break out to 400 gigabit electrically on the switch or router side to give you more flexibility. As we get into the native ZR Plus channel modes, though, you'll see there's so many of them, and the reason there are really depending on the use case, depending on the loss of the fibre, i.e. the total distance, typically, and also the bandwidth. So you'll actually see that as we increase in the channel modes here, they're actually decreasing in bandwidth. So at some point we have to compromise going from 400 gig worth of bandwidth down to 300, down to 200, and then down to 100 for the longest of links. So I'm not going to read this slide out entirely. The slides are available online, but you can see that we have increasing kind of loss ratios as we go down the channel modes, and that bandwidth compromise there. We do also need a line system. So in theory, with a line system, you can get 48 to 64 channels of this down the line system. It does require amplification. So typically that's going to be EDFA amplification, but as you'll see shortly, we can improve on that. And so, similar to ZR, the actual transmit power of these transceivers are still quite low. And again, that's due to the thermal and cooling limitations. So we're still going to be transmitting around -10 dBm. Same grid, so 75 or 100 gigahertz spacing, nothing new there compared to ZR. So curiously, it mentioned around amplification. If we're using EDFA amplification, which is probably what you've used traditionally for longer links, we can actually still go really long, right? So with EDFA only, we can get up to 480 kilometers, which for those of us in the UK, with this being UKNOF, I'd say is a pretty good distance. But if you do need to go more, you can actually use EDFA and Raman amplifiers to get longer distances there, or as mentioned, you can compromise on bandwidth. So you can downrate your 400 gig link to say 300 gig, and that gives you a lot more distance. So in our real world example, we did already have a line system. So this was a brownfield deployment with, as it happened, Nokia WDM equipment. We do need a preamplifier for the line system to bring it up from that -10 dBm that I talked about. And as it happens, we were terminating these on Arista 70-80 R3s. So we're using ZR optics. So in this case, it was a QSFP-DD, which is the smaller and hotter of the form factors. And we have two different lengths of link. So we have a shorter link, so again 40 kilometers, that we are configuring ZR Plus on this time. And we also have a much longer link, which is a 750 kilometer link, shown in green here. So in terms of configuration, we still need to configure the frequency. That is the channel we're using, same as ZR. So in this case, we're configuring 193.4 terahertz. But there are also two other important pieces of configuration. The next is the application mode. So in this case, we're going to be using application mode 5 here. Application mode 5 is 400 gig. And we have a host format, which is what it looks like on the fiber, which is native 1x400. But you'll see here actually, native. It's a native 400 gig link electrically as well. What is more interesting is you'll see this transceiver here consumes 23.75 watts. So if you're familiar with your kind of 1 and 10 gig transceivers, we're using a lot more power here. And as it happens on this particular Arista device, we do have an officially maximum supported slot power of 20 watts. So in this case, we had to enter the transceiver power ignore command. This is not something I would always recommend, and so do please check the datasheets, talk to your vendors before configuring this. So, what does this look like? Well, the good news is we seem to have a link up, which is always a good start. Case temperature, 54 degrees, so hot. Still probably don't want to be touching that with my bare hands. Channel power, received channel power is looking okay, minus 11 dBm. 0 post-vec error frames, which is always good, always what we want to see. Chromatic dispersion, now this is the short link, so 600 picoseconds per nanometer looks about right. We can do the maths on that and get it, again, 17 picoseconds per nanometer per kilometer. We can actually translate that to roughly a 40 kilometer link. And yeah, OSNR looks good, and we can see the frequency. Now looking at the longer link here, for the longer link, the 750 kilometer link, we're actually going to be using channel mode 7. So what that means is we are going to be reducing the bandwidth down from 400 gig to 300 gig. But in terms of presentation electrically on the link, that presentation is actually going to present itself as 3 100 gig lanes. So as it happens on our device, we do need to hard code the speed. So we need to hard code the speed of a 100 gig -2. The -2 is simply a representation that it's using 2 electrical lanes to form each 100 gig link. So it's actually 2 lanes of 50 gigahertz on the PCB that are coming from that transceiver per link. So again, we need to mention the channel group per link, which is channel group 7. And I haven't highlighted it in yellow here, but we do also need to still do transceiver power ignore, because of course it's still a ZR+. It's the same type of ZR+, and therefore it's going to be consuming 23.75 watts. But yeah, everything looks good. As mentioned, because we're doing 3 by 100 gig mode here in show transceiver status, we can see we have 3 links up, Ethernet's 36/1/3 and /5, just to nominate the lanes there, and naturally the /7 is not connected. Again, case temperature looks good, post-vec error frames ratio of 0, OSNR of 21.5 dB, which, as you can see for channel group 7 here, is within the range. But if I were to have chosen one of those higher channel groups, we may have either not had a link up at all, or we might have started seeing errors, hence the need to move down to group 7 there. So in summary, I think ZR Plus for 400 gig is a really fantastic kind of longer distance solution. So in the UK, that can definitely cover around the UK, much of connectivity to Western Europe and so on. But of course, the current solutions today are low transmit power of roughly minus 10 dBm. So of course, you do need a line system. You do also need a preamp potentially for those existing line systems. The other key takeaway is they do use auto power. Now we've found actually, depending on the transceiver, they can be quite variable, somewhere between 18 watts and 25 watts. So do be careful of that. And of course, you do speak to your vendors to ensure you have the support for that high power. Thank you very much.
Well, thank you, David. That was really interesting. So, any questions in the room? Want to come up to the mic? Line up at the microphone? Can you come up to the microphone and read them out? Please, can you also just state your name and affiliation as well, so we can hear it on the webcast?
Anne Johnson on the program committee. So when one is trying to buy these things, what's the approximate lead time, and what do you find are the scaling characteristics in terms of being able to get these from the suppliers?
That's a very good question. So I'm not probably the best place to talk about lead times. I know they're a problem across the industry. Transceivers do tend to be a little bit better than most. Personally, I work for a vendor who happens to manufacture transceivers, so obviously I have to recommend my own. But given the kind of more neutral nature, I'll say there are many suppliers out there.
Greg Choules, ISC. Is it healthy running these things that hot? Surely it's not good for the noise level or for the longevity of the product.
That's a very good point. So they are certified to run at that temperature. What I will say is, if you think there's two form factor standards, there's QSFP-DD and OSFP. I personally, this is not a vendor recommendation, have a preference for OSFP because it is a bit bigger. You can get a bigger heat sake on. You can bring that temperature down a little. And I did see a shocking stat actually, and this is off the top of my head, so I haven't verified this exactly, but I think it's something like every 10-degree increase in temperature results in a doubling of halving of MTBF. That is the failure rate of the product. So raising it from 50 degrees to 60 degrees could potentially halve the MTBF.
Could people look into active cooling and bringing it down to sort of more like room temperature? And I don't know, just a suggestion.
That's a really good question. I suppose if you had a device that you knew was dedicated for ZR and ZR Plus, it'd be much easier to do. Typically, I'd say most switches and routers, people are putting these things in kind of more general purpose switches and routers that, maybe 100,000 products might only have SR optics in,
yep.
And then the 101th is using it. So it's tricky. It's tricky.
All right. Thank you.
Ivan Beveridge, IG. You primarily mentioned QSFP-DD.
Yes.
And obviously just mentioned the OSFP. Does OSFP give additional power, or is it just a kind of the ability potentially to run at a lower temperature?
So power is primarily informed by the ability to cool it. There is, as mentioned, there is a slightly better ability to cool OSFP. On our products in particular, they're both up to 24 watts where it's supported. So there's no difference officially. But to the earlier point, it may be it just runs at a slightly lower temperature, and therefore you might have a better MTBF, better failure rate moving forward.
Okay, because the question, I guess, which I didn't, I wasn't clear on, would an OSFP, is that likely to give a further distance compared to a QSFP-DD in the same situation?
No is the short answer. Certainly for our products, which is if they're both rated to 24 watts, they're both going to have the same transmit power. Potentially there could be a solution, I guess, where you could have a higher transmit power OSFP. It's not something I've seen in the industry.
Thank you.
Thanks, Simon.
Hey, David. Tom Hill from BT. This is probably on top of all the other questions that have come before me, and I considered not actually coming up to the microphone. But given that we have two standards here, one of them has a slightly better surface area, but they're mostly rated for near enough the same wattage, power consumption, etc., etc. Do you see a situation where, because I've seen a lot of designs with QSFP-DD, a heck of a lot of vendors aren't using OSFP. Do you feel as if you're going to be in a situation where you're going to struggle with supply and demand for OSFP, and it will naturally fall to the side, even if it is, in theory, better? I mean, it's the trade-off of density on the faceplate, right?
Yep.
Where's the future? Are we going to have two standards, or is it going to fall to one?
My view is it will fall to OSFP on the basis that DD, I think DD works very well. You have the backwards compatibility. But if you cast your mind forward to maybe in a world where we have 800 gig and 1.6 terabits and who knows what else, I would hope OSFP at least is a multi-generational form factor. Whereas I would imagine DD is more of a single to two generation form factor. But again, that's my personal view.
We'll come back in 2 years and we'll see what happens.
Yeah, I'll be presenting 800 gig. We'll see.
That'd be good fun. Thanks.
Thanks, Tom.
I think there are no questions from online. Okay, then that's it. So yes, thank you very much, David. Thank you. Really good talk.